Okay. We will get started. So we've finished grading your exams. There were so many exams, but we finished. And here is here's the distribution. I'll post up the I don't know, this graph on CCLE, and you can check. So this is the distribution of scores. What we did is at the very end, I decided to add 8 points to everybody's grade. Okay, and so that's why we have the max score is 107. It's above 100. So we added 8 points to everybody's grade. So the grade that's on CCLE already reflects the additional 8 points that we added. Okay, and with that, our median is 80. And you can see the kind of the stats there. I do want to say a few things about exams and grades and scores and stuff in general. Okay, first of all, it was a tough exam. All right, there were a lot of weird details and stuff that we tested on, and so that. So don't feel bad if your score was not as high as you would have liked it to have been. And you know what? I always say this, but don't let your self-perception or value of self or whatever be subject to scores on an exam or scores or grades in a class. Okay. I get it. It feels good. Like when you score well on an exam, that feels good, and when you score poorly on an exam, that also feels bad. Okay, and I understand that. But at the same time, each one of you is a full and complete person already as you are, and your value as a human being is not determined by scores or grades. Okay. I know you spend a lot of time and energy on your classwork and coursework, and so your coursework will feel valuable and precious to you because that's where a lot of your energy is going. But at the same time, in the grander perspective of things, these things they do not speak to who we are as human beings. Okay. So anyway, this is this. My other consolation is that the midterm exam is worth only a small fraction of your grade. It's like 20%. Okay, and so there's 80% of the other rest of your final course grade comes from all sorts of other stuff. The homework and the final and other things like that. There's lots of other things at play. So if you didn't do that, great. There's still plenty of opportunity to recover points and things like that. Okay. The plan is to have the TAs return the exams to you in discussion next week. Okay. So go to discussion and you'll get your exams back. Let's see. What else do I want to say? So when we give you your exams back, please keep them to yourself. Don't take pictures of them and post them online, or don't be giving them to other students and things like that. That's not the intention of returning the exam. That's not the intention. Most exams I actually hold on to and keep myself for safekeeping, but this exam I'll choose to return to you. But please don't. There's some trust going on here, and every now and then I do a search for myself on Course Hero, and it always disappoints me to find my stuff being posted. Okay, because on a lot of my notes I'll write like, for personal use only, please do not post or distribute, and yet somebody has betrayed my trust here, okay? And just so you know, distributing course material, especially stuff that notes that your professors have created, is a violation of university policy, and should the professor pursue it, they can refer you to the Office of Student Conduct, and you can be disciplined for doing stuff like that. You know, I don't want to do that, but I just ask that you guys respect my wishes and things like that. Okay, so don't. So we'll return the exams to you in discussion, but please don't post them online. Okay, or distribute them or put them in test banks or things like that. Okay. Are there any questions about this stuff? Okay. All right. Well, okay. I think at the beginning of the course I said the course is kind of thematically split into two parts. The first part focusing heavily on R and R programming, details of its data structures and functions and control structures and things like that. And then the second half will start to focus on the numerical aspects of computational statistics. Okay, and so a key point that we have to kind of start off with is the representation of numbers on a computer. Now, if you've taken a CS course, this is probably old news for you, but many of you have not taken some kind of CS course, and so this will be kind of just our introduction to floating point numbers and their representation in the system, because this is going to be very important. Okay, and so we will start here, and let's see. Okay, so as far as math goes, you guys have learned about real numbers, right? And this is, I don't know when they first introduced the concept of real numbers to you, but probably middle school or something like that. And they said you have your natural numbers and your integers and your real numbers, and then at some point you learned about complex numbers and stuff like that. But a lot of times we're dealing with real numbers, and real numbers go from negative infinity to positive infinity. And the important aspects of real numbers is that there are infinitely many real numbers. And if you pick two spots on the number line, there's infinitely many real numbers between any two positions on the number line. So you can say 0 and 1, and there's infinitely many values between 0 and 1. Okay? And so there's perhaps most of the real numbers will have an infinite number of decimal places. Values like pi or e or the square root of 2, they have infinite values after the decimal point. And if we wanted to represent any of these numbers on paper in decimal form, we cannot represent their exact value in decimal form. Okay, we can only represent approximations. We can write, for pi, we can write 3.14, but that's an approximation, and you guys are aware of that. Even if we write a whole bunch more decimal places, right? 3.14159265535, that's still just a decimal approximation. And even if I printed out, a million sheets of paper up to the billionth digit of pi, that is still just a decimal approximation, and it's not the actual value of pi. And because of that, because we're only able to get approximations of real numbers, this has some profound implications on many of these mathematical rules that have been ingrained into us and something that we take for granted. So everything you've learned in algebra about all of these math rules no longer apply when we're doing stuff on the computer, okay? And that is because in a computer, we have a finite amount of memory and a finite amount of storage. You might have 8 gigabytes of memory, but 8 gigabytes of memory is not infinity, okay? And so you might be able to represent a lot of values, a lot of decimal places, okay? You can represent all, the billion digits of pi. That can fit in your memory, but it's not the exact representation of pi, okay? And even if you filled out all 8 gigabytes of your memory with a bunch of decimal digits of pi, it is still just an approximation, okay? So, we cannot represent any of these real numbers that have infinitely many places. And so, so I'm going to just kind of give you a little kind of example that maybe you guys are familiar with, maybe maybe not. Here, let me pull up this camera here. Is this gonna work? Okay, so I have a calculator, right? This is an old school calculator, okay? This cheapo calculator. And so what I'm going to do is, this is tricky. Okay, I'm going to do 10 divided by 3, okay? And what will happen when I do 10 divided by 3? Okay, I'm going to get what? 3.33333, okay? So this is 10 divided by 3 on the calculator, okay? Now, I'm going to take this number and multiply it by 3. And what will I get? Okay, so we're going to take this number, I'm going to multiply it by 3, and I get 9.99999, okay? And that's because this calculator is only able to represent 8 digits at a time, okay? And so it's not able to represent 10 divided by 3 exactly, okay? It has to represent it with an approximation of 3.333, and this being a stupid calculator doesn't know that there's infinitely many more 3's after the decimal place, okay? And so it just sees this as technically 3 and what is this? 3,333,333 10 millionths, okay? And so when I multiply this by 3, it doesn't give me 10, but it gives me 9.99999, okay? On the other hand, so if I did 10 divided by 3 multiplied by 3, I don't get 10 back, okay? On the other hand, if I change just the order of those operations and I do something like 10 times 3, 10 times 3 gives me 30. There's no surprise there. And if I take that number and I divide by 3, I get 10 back, okay? So 10 times 3 divided by 3 gives me 10, but 10 divided by 3 and multiplied by 3 doesn't give me 10, okay, on the calculator. And we can kind of, we see it and we kind of get it with the calculator because we understand that this thing is only able to store 8 digits at a time, okay? And pretty much the exact same concept, exact same idea happens on the computer as well, okay? It's a little bit more hidden from us because the computer does some automatic rounding and it stores more digits, but at a baseline level, the same idea of trying to represent a real number which might have infinitely many decimal places with a finite number of digits means we're only getting approximations, and when you do calculations with those approximations, a lot of our fundamental mathematical rules fall apart, okay? So let's, so what we saw is 10 over 3 gives me this, and when we multiply by 3, we get that, okay? And on the other hand, oh, this is supposed to do 10 times 3, we get 30, and we divide by 3, and we get 10, okay? So a mathematical rule, which is basically the associative rule, okay? Whether we do x divided by a and then multiply by a, or whether we do x times a divided by a, that shouldn't matter in math. It makes a difference in the computation, okay, in a computer, all right? And so these rules that we kind of hold dear no longer apply when we're doing computational math, okay? And so we get, so I can actually demonstrate this even on our computer here with R, okay? So so here you can try this out. Here maybe it will be better if I just do it for you. Okay, I'm going to create 3 values. Okay, we're going to say x is 0.1. Okay, x is 0.1. And I say y is 0.2. Okay, y is 0.2. And z is going to be 0.3. Okay, z is this. So again, x is this, y is 0.2, z is 0.3. Okay. So if I do x plus y, I will get 0.3. There's no surprise there, right? Okay, so x plus y, x is 0.1, y is 0.2, x plus y gives me 0.3. So then I can ask, is x plus y, is that equal to z? And this gives me false, right? So I say, okay, well, what was z again? Z is 0.3. And what is x plus y? X plus y is 0.3. And if I try this again, is x plus y equal to z, equal to z, I still get false, right? And this is, all right, well, is 0.3 equal to 0.3? That's true. Is z equal to z? That's true. X plus y, is that equal to x plus y? That's true. What is x plus y? 0.3. What's z? 0.3. X plus y, is that equal to z? And I get false. Okay. What's happening? What's going on here? Yeah, so what we can do is we can do something. I can do options. Digits equals something like 17. Okay? And what we can see is that x, even though I told x was equal to 0.1, in the computer, it's actually stored as 0.10000000001, okay? And that's because we can't represent, in the same way that we're not able to represent 10 over 3 exactly on this calculator, we're not able to represent 0.1 exactly on the computer, okay? Similarly, y is not exactly 0.2, but it's an approximation 0.20000 something, right? And if I say, well, what is x plus y? When we add these two together, we get 0.3, and somehow when we add these two together, it ends up with a 4, okay, over here, okay, which feels weird, but that's what happens, okay? And if we ask, well, what is z? It's different. It's 0.2999999, okay? And the issue here is that we are not, again, just like on the calculator, we can't represent 10 over 3 exactly. It can only be represented as 3.33333, and it stops. We are not able to represent 0.1 or 0.2 exactly. In binary, it gets represented as something else, which is very close, but not exactly the same. And so when we test, you know, is x and y, is that equal to z, the computer comes back and says no. Okay, and so inside the computer, the computers use binary, which means every bit is either a 0 or 1, and this allows us to represent powers of 2 easily. Things like 1/2 is just 2 to the negative 1. We can represent that exactly in the computer. Okay, a quarter, you know, 1/16, whatever it might be, powers of 2 can be represented exactly, whereas other values like 0.1 or 0.2 can only be represented with a binary approximation, okay? So 0.1 plus 0.2 equal 3 is going to be false, and that's because the binary approximation of 0.1 plus the binary approximation of 0.2 is not equal to the binary approximation of 0.3. So everything that gets stored in the computer, because we only have finite amounts of storage and memory for each number, just becomes an approximation, okay? So maybe it's good to just review counting in binary. I know a lot of you guys already know this, but here if I use 4 bits to represent a decimal number, You know, 0 starts off with 0, 0, 0, 0. 1 is 0, 0, 0, 1. And so, you know, this first place is the zeros place. The next is, this first place is the ones place, which is 2 to the 0. This next place is the 2's place. Here is the 4's place, 2 to the 2. And lastly, we have 2 to the 3 for the 8's place, okay? And so with 4 bits, I can represent 16 different values, and those are going to be 0 through 15. So I go 0, 0, 0, 0, 0, 0, 0, 1. And at 2, it goes to 0, 0, 1, 0. Okay, 1 in the 2's place, a 0 in the 1's place. 3 is a combination of 2 and 1. So I have 1, 0, 0, 1, 1. And at 4, it rolls over and I have 1, 0, 0. 5 is the combination of 4 and 1, so 1, 0, 1. 6 is 4 and 2, 4, 1, 1, 0. And 7 is going to be 4 plus 2 plus 1, 1, 1, 1. Okay? And then, so if I want to count higher and go to 8 through 15, you will notice that these numbers are exactly the same as these numbers, except we've changed the leading digit from 0 to 1, okay? And that's because this leading digit represents 8, and so we can think of 8 as 0 plus 8, so we have 1 plus the other 3 digits, 0, 0, 0, okay? And 9 is 8 plus 1, so I'm going to take this 8, which is 1, 0, 0, and add this, and I get 1, 0, 0, 1. 10 is 8 and 2, so 1, 0, 1, 0, and so on and so forth. This column is exactly the same as this column, but we've added a 1, okay? And if I wanted to keep counting further, going up to 16 up through 31, I would just take all of these things, and I would add in a 5th digit, which is going to be leading with a 1, and so on and so forth. And it just kind of repeats this pattern, but we're just kind of appending additional 1s in the front, okay? So that's just counting in binary. Okay. And so we could use something like this to represent integers and things like that. But on the computer, we want to be able to represent basically fractional numbers, okay? So numbers smaller than 1, numbers in between 1 and 2, and things like that. And so we use a floating point system, okay? Everything in R that's type double is a floating point number, okay? So when you see type double, that's a floating point number. And floating point is basically, is basically the computer implementation of scientific notation, okay? So if you remember in, I don't know when you learned scientific notation, maybe chemistry class, maybe, you know, some other math class. Everything is represented with a mantissa multiplied by an exponentiated base, right? So in decimal form, it's going to be m times 10 to the n, right? And what are the rules about that mantissa? The mantissa has to be a value between what and what? What's that? 1. Yeah, 1 and basically 9.99999, right? So the leading digit has to be between 1 and 9. You cannot have a 0 for a leading digit for the mantissa, and you can't have anything bigger. You can't have 10. You can't have 2 digits for the leading digit there, okay? And so for binary, what will we have for the leading digit? 1, okay? Because I can't have more than 1 digit for the leading digit, okay? And I can't have a 0 for the leading digit, okay? So anyway, but in binary, it's going to be m times 2 to the n, because we're now in base 2. So it's going to be m times 2 to the n. So that's going to be our floating point system there. We are going to talk about the IEEE 754 standard for floating point numbers. So back in the day when different companies were making computer chips, okay? Now, I don't know who makes computer chips, right? There's Intel, there's AMD, there's Snapdragon or Qualcomm, right? They make computer chips, and Apple makes their A series chips and stuff. So everybody makes these different computer chips. And they came out, IEEE, the engineering organization, said we need a standard for how to represent numbers. And so they came up with this standard for how numbers are represented. This is implemented at the hardware level, okay? It's not subject to which software you're using or things like that, okay? So if I have an Intel chip and you have an Intel chip on your Mac, the computer, the values are represented in the exact same way, and actually pretty much all computers use this. There was a revision in 2008, but it pretty much contains everything that's specified in the 1985 version. They just added a couple things to it. So for learning, we'll learn the original specification of floating point numbers, and this Wikipedia article is very good, and we will take a look at that. Okay, and so I am now going to transition to using my drawing tablet and do some handwritten notes here. So you might actually have to get out some paper to take notes. Okay, but then again, all of these notes will also be available on the. I'll post this as a PDF. Okay, so let's talk about, so in the IEEE 754 standard, okay, type double uses 64 bits to represent a number. Okay, so each bit is, basically a 0 or 1, okay? And so we have 64 of these things. Somewhere on the computer, on the computer chip are these tiny little transistors that either are stored as 0 or 1, okay? And these are like little nanometer big things. They're tiny, tiny, tiny things, but we use 64 of these bits to represent a number, okay? And so where did my notes go here? Okay, so what we have is of those 64 bits, okay, they get split into 3 parts, okay? 1 bit for the sign of the number. Okay, 0 for positive, 1 for negative. Okay, and then we have 11 bits for the exponent. Okay, because again, we're representing things in scientific notation, binary scientific notation. So we're going to have mantissa and an exponent, and so we have 11 bits for the exponent, and the remaining 52 bits are for the mantissa. So this is how floating points are used on the computer. And for illustration, we are going to have a mini float, okay? So for teaching, I will do a mini float, okay? And we're going to have 8 bits to represent numbers. Okay, with kind of following the same system as following the same standard. Okay, except this time our 8 bits will have 1 for the sign, and we'll do 3 for the exponent, and the remaining 4 for the mantissa. Okay, and so it'll be kind of, so I've got 8 bits, and it'll go go like this. Okay, and so maybe we'll just talk about representing. First, we'll talk about representing our decimal values in binary, and then in binary scientific. Okay, so just some values in decimal, binary, and binary scientific. Okay, so binary scientific will be m times 2 to the n here. Okay. All right, so let's say we have the number in decimal. We have the number 0.5. Okay, so 0.5 is equal to 1/2, or this is 2 to the negative 1. Okay, and so in binary, we would represent this as 0.1, okay? Because in binary, this would be the 1's place, which is basically 2 to the 0. This is the 2's place, which is 2 to the 1. And this would be the 4's place, 2 to the 2, okay? The point is technically a binary point, not a decimal point. I'm just going to call it point, though, all right? And then over here, this would be the halves, 2 to the negative 1, the quarters, 2 to the negative 2, and what would I have here? The 8ths, 2 to the negative 3, and so on and so forth, okay? So to represent the decimal value of 0.5 would be represented in binary as 0.1, and in binary scientific, what would I have? This would be 1 times 2 to the negative 1. Is that okay? All right, let's just try another one here. In decimal, let's say I have 0.75, okay? 0.75 is equal to basically 1/2 plus 1/4, right? So in binary, how would I represent this? 0.11, right? I'm doing 1/2 plus 1/4, 0.11. Okay, and so this becomes in binary scientific, we would have 1.1, and I moved the decimal place over 1 spot, so I would have times 2 to the negative 1. Okay, so 1.1. If you think about this, 1.1 in binary is 1.5. And I'm multiplying it by 2 to the negative 1. I'm multiplying that by 1/2, and I would get 0.75. Right. All right, let's try something. All right, so in decimal, let's say I have 6.625. Okay, so let's break this up into powers of 2. This is equal to what? 4 plus 2 plus 1/2 plus what? 1/8, okay? So 6.625 is 4 plus 2 plus 1/2 plus 1/8. So in binary, how would I represent this? So I would write 1 for the 4's, 1 for the 2's, 0 for the 1's, 110.101. Is that okay? In binary. 110.101. All right, and then in binary scientific, this becomes, so I write the exact same numbers, 110.101. Where do I put the point? After the first digit, okay? So I have 1.10101, and this would be multiplied by 2 to the 2, because we moved the point over 2 spots. Good. All right. So we can now we can take decimal values and represent them in binary, and then turn them into binary scientific. And so what we want to do is for our floating point representation is we want to turn this binary scientific thing into something that we can represent using our combination of the sine, exponent, and mantissa. Okay, so we want to represent, kind of binary scientific with sine, exponent, and mantissa. Okay. All right. So in our mini float, we have 3 bits for the exponent. Okay. So I can represent how many unique values? 8 of them. Okay. 2 to the 3 is 8 unique values. Represent up to 8 unique values. And so let's just kind of list them out. With 3 bits, I can have 0, 0, 0, 0, 0, 1, 0, 1, 0. Need to space them out a little bit better. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. And so regular decimal, in decimal, this would be 0, 1, 2, 3, 4, 5, 6, and 7. So I can represent 8 values, 0 through 7, in decimal. But one issue is that these are only positive, okay? We want to be able to represent negative values as well, okay? So decimal is only positive, and I need negative values. So what we're going to do is we're going to use a biased scheme. All right? The biased scheme says we're going to take each thing and we're going to just subtract 3. So 0 gets shifted down to -3, 1 gets shifted down to -2, 2 gets shifted down to -1, and we get 0, 1, 2, 3, 4, okay? And so now I can represent both positive and negative values ranging from -3 to +4, okay? Now we can represent negative and positive values. Okay, we just shift the values by our bias. Okay, and so what we use for the bias in general, the bias will equal 2 to the n minus 1, where n is equal to the number of bits in the exponent. Okay, so if we do 2 to the 3 minus 1, this becomes 2 to the 2 minus 1, 4 minus 1 is 3. So we have bias is equal to 3. And 3 just means we're going to take our regular decimal representation of the binary thing and shift it down by 3. Is that okay? So here we have 3 bits, and so our bias is going to be 3. In the regular 64-bit representation, we use 11 bits for the bias, so we're going to have a bias of 1023. Okay, you do 2 to the 11 minus 1, 2 to the 10, 1024 minus 1, 1023. So we have a bias of 1023 in the regular floating point system here. Okay, and now we have 4 bits for the mantissa. Okay, and so the mantissa in kind of binary scientific. Okay, so in scientific notation, the leading digit cannot be 0. Right? And in binary, there's only one other digit that's not 0. Okay? If it's not 0, it must be 1. If the digit is not 0, it must be 1. Okay? So we can always assume the leading digit in the mantissa is 1. Okay? So our 4 bits represent basically 1 point. These are your 4 mantissa bits times 2 to the exponent. Okay? So so we can take our 4 mantissa bits, and we can always assume that the leading digit's 1, because in scientific notation, you can't have 0 for a leading digit. And in binary, if it's not 0, it has to be 1. So we're going to use our 4 mantissa bits here, and then the 3 exponent bits go into here, and then there's going to be a sign bit over here, right? For positive or negative. Okay, so let's just try out what something. Let's do an example. Okay, so if the floating point bits are let's say they are 0, 1, 0, 1, 0, 1, 1, 1. Okay, so this is our sign, the exponent, and the mantissa. All right. What we have is we're going to have sign is 0, so the sign is positive. 0 equals positive. So we're going to have 1 point, and then the mantissa, I'm going to, we take the mantissa part, 0, 1, 1, 1. So this is from the mantissa, times 2 to the exponent. Okay? What is our exponent? Okay? Our exponent bits are 1, 0, 1, which is equal to what in decimal? 5 in decimal. Okay? But how much is our bias? Our bias is 3, so 5 minus 3 is equal to 2. The exponent is 2. Okay? So this is 1.0111 times 2 to the 2. Okay, I guess it's positive. Positive 1.0111 times 2 to the 2. Right? And so now we have a couple ways to do this, right? So we can just say, all right, what is this? This is going to be 1 plus 0 halves plus 1 quarter plus 1/8 plus 1/16. Okay, that's what this part is. Times 2 to the 2, or which is basically 4. Okay, so I'll just replace that with a 4. Okay, and so when we multiply this out, this becomes 4 plus 0 plus 1 plus 1/8 times 4 is 1/2, and 1/16 times 4 is 1/4, and this gives me 5.5 5.75. So this is our this is what we have. We have so 0. What was it? 0. When did I have up there? 101. 101. 0, 1, 1, 1. In bits, it becomes 5.75. Okay, so you have 8 bits turns into 5.75. Is that okay? If you wanted to do it before, like if, I guess alternatively, we could have also done 1.0111 times 2 to the 2, and we could have said, well, this means we're going to roll the point over 2 spots, and we would have 101.11, and this would be 4 plus 1 plus 1/2 plus 1/4, and that's also 5.75. Okay, so you can move the point first, or you can do it this way and multiply it out. It's all the same. Moving the point over is the exact same thing as multiplying by 2 to whatever power it is. Okay, so here we can represent values. Let me just say something about the sign bit, okay? So we have a sign bit. Sign bit is either 0 or 1. 0 for positive, or 1 for negative. And what that means is any value we represent with the other 7 digits, or we represent with the other 7 bits, will have both a positive and negative version. Okay, so I guess the only weird thing is that we will have there is both a positive and a negative 0, okay? Okay, but that's just a little bit of an artifact here, okay? All right, I'm going to just squeeze in one more thing with our last 2 minutes. Okay, so we have special values, and we'll cover more on Friday because there's still more to say. But here's a few things about special values. Okay, if you have all ones in the exponent and all zeros this becomes equal to infinity. Okay, so this is infinity, and thus you have, this will become negative infinity. So, at least the computer's representation of infinity and negative infinity, okay? And on the other hand, if you have all ones in the exponent, but something other than all, not all zeros in mantissa, this becomes nan. Okay, this is how the computer represents not a number. All right, and so all nans are type double, right? And this will, if you do 0 over 0, that will become nan. Infinity over infinity, that will become nan. There's other things that end up as nan and stuff like that. But anyway, we'll stop there for now, and we'll keep talking about this on Friday.